Hello guys, welcome to Friendsintech Automation YouTube tutorials. And I will always start my videos with this kind of pictures. Now, just explaining industrial automation levels because you want to be automation engineer, so you need to understand the hierarchy of automation. You have to appreciate the hierarchy of automation. So level 0 is field level. So this is where you get your sensors. You have your sensors and actuators. Then level number 1 is control level. You have your PLCs and DCS. Level number 2 is supervisory level. You have your SCADA systems and HMI. Level number 3 is production level or manufacturing level, where you have your manufacturing execution systems, MES. Level number 4 is enterprise level or business level, where you have ERP systems such as SAP and Odoo. Now, that's aside. So in today's video, we want to explain something important. Our previous video, you can find the link up here. So our previous video, we explained how you can create your first project in TI portal and how you can add a CPU, power supply, IOs modules, that is digital inputs, digital outputs, analog inputs, analog output cards, and communication card. Now, this is what is called modular PLC. This is what you're seeing here. This is a modular PLC, okay? It's a modular PLC because the CPU, power supply, and I/O cards resides in different hardwares, in separate hardwares, okay? Then we have compact PLC like Step 7 1200. Step 7 1200 is a compact PLC. Why? Because you have IOs and CPU residing in one hardware. All right? You have IOs and CPUs residing in one hardware. That's a compact PLC. But this here is a modular PLC. Now, in this video, we want to explain input units and output units. You have to really understand what is the input unit and what is the output unit. Why am I using DI32 by 24 VDC? Why am I using DI24 by 120 or 230 VSC? How does it work? What's the difference between the two? Why one is 230 and the other one is 24 volts DC? What's the difference in terms of circuitry of those two cards? Now, and we have analog cards. Like for example, here you have AI 8 by 14 bit. You have to understand what is the meaning of 8 there, or what is the meaning of 16 bit, and how is it different from AI 8 by 16 bit. One is 14 bit, the other one is 16 bit. What is the difference? Then we have analog output card. So what is the difference between these two cards? So that's what I want to explain. What I'm doing here is that I want you that when you visit this channel, you are getting out with complete information on PLCs. All right? Now let's get started. So the first thing here, we have signals, okay? You know, PLCs, we have analog and digital signals. So that's the first thing. So signals, so we can divide signals into, of course, I know you can divide into analog signals, digital signals, and discrete signals. But let's just say digital, okay? Digital signals, okay, fine. There's no need to rewrite signal there again. Digital signal. Now, so you have PLC. So PLC can handle analog and digital signals. So for PLC to handle digital signals, it will need a digital input card or a digital output card. All right. So inside digital here, we have, again, this one we can subdivide into two. So the first we have digital input module or input card. Then we have digital output card. And of course, analog we have analog input cards and analog output cards. Perfect. That's something you should know. All right? That's something you should know. Now, under digital input cards, we can have one for 24 volts DC cards, and we can have 230 stroke 120 VAC cards. All right. Then under digital output cards, we have this here. We have relay based digital output cards, and we have Triac based digital cards, and we have transistor based transistor. Of course, we have, it can be a 24 or a 230, it doesn't matter, but relay Triac transistor matters. So again, when you are selecting, because this is common with compact PLCs, you'll be told that these outputs of this compact PLCs, this is relay outputs or Triac outputs or transistor outputs. There's a difference. Now, let's start with digital input card. Digital input card. So digital input card, so of course this accepts digital signals. For example, you can connect a push button. Push button will give you 0 ones. All right, a push button will give you 0 ones. So, but we say that it can be AC or DC. That's why in this setup here, we have DI 120/230 VAC or VUC. Then we have DI 32/24 VDC, DC. So one is DC, the other is AC. What is the difference? That is what I'm explaining, okay? The difference between the two. Now, the difference is in terms of circuitry, the electronic part, okay? So this is the circuit for AC and the circuit for DC. Now, this is here. I don't have to repeat this again. So this is discrete or digital AC input module. So for example, you can connect a push button to this card. So what will happen, we need to rectify this 120 VSC or 230 VSC to digital voltage. Then we add Zener diode for level detection and protection. Then we use opto isolators. So the work of opto isolator is to isolate the internal circuitry of PLC from high voltage high external voltage. That's the work of optoisolator there. Circuit. Now you have your push button here. Then it passes through the filters. Then you have a rectifier. This converts AC to DC. Then we pass it to an optoisolator with light emitting diode there. So this light emitting diode will dislodge electrons on the surface of this transistor, therefore providing 5 volts to this digital logic circuit. That is how this module works, this module here. So that is how these modules work. This 16 by 120 stroke 230 VSC. What about one for DC? So with DC, the only difference here is that we are removing this here. We don't need to rectify DC again. So we are only removing rectification. So we are just connecting it direct. So we are giving 24 VDC here. Then we are removing this guy here. We are removing the rectifier. So we connect this directly to optoisolator. Then of course, the other side of transistor gives 5 volts to the microprocessor. That's it. Now that is the circuit. So that is the difference between DC input, digital input card, and AC digital input card. All right. Now, what about output card? Because if you take a look at output, this here, if you take a look at output, digital outputs, we have one for 24 volts and the other one for here, this one here, for 120 stroke 230 VAC alternating voltage. Now, what is the circuit for this? So this is the circuit. So this here, the signal is coming from the microprocessor, and the microprocessor is giving 5 volts, 0 to 5 volts. So 0 to 5 volts goes to optoisolator, and this is from optoisolators to electronic switch. Now this electronic switch here can be a transistor, can be a triac, and can be a relay. Then from that to your load. Now, when selecting digital output module, you have to take care of this electronic switch. Is it a triac? Is it a relay? Or is it a transistor output module? Now, this is the circuitry for triac based digital output module. This here. So we are using triac. There. So we are saying triac is a bidirectional, consists of 2 thyristors or 2 silicon control rectifiers. Now the signal is coming from the CPU to your optoisolator. Now this optoisolator will provide the firing signal to your triac. So when triac is sent into conduction mode, this is what happened. The voltage or the current will flow from L1 all the way to your load here. That's how it works. So triac behaves like a switch. It's just a switch. But the triggering signal is coming from the optoisolator. Now, instead of using triac, remember triac is used to switch only AC loads. Only AC loads. So if you have a digital output card that is triac based, then just know that you want to switch AC loads only. AC loads only. Such things like solenoid valves or maybe lamps. Okay? Now, what about if it is transistor or a relay based? This is what we'll have here. So if it is relay based, let's start with the relay based. So I start by drawing optoisolator. Now this is opto isolator, okay? This is opto isolator. That is opto isolator, right? Now from opto isolator, we want the switching signal from opto isolator because this is the signal from the CPU. Now, this is what we'll have. So this will send this signal to the base of the transistor. Let's just use BJT transistors. Just a minute here. You can just put indication diode there that the output is high. Then this is the base of transistor. That's it. Then you have it that. Have it like that. But now there's a problem when using transistor. So transistor here can be NPN or PNP. That is the problem with transistor, okay? It can be NPN or PNP. So let's start with NPN transistor. So this is an NPN transistor. So if it's an NPN transistor, so this is where we can connect load. So this is our load. And this is the positive voltage. This is the V positive. Let's say 120 VAC. All right. Then this other section, we just connect the two. Then this here is there's negative, V negative. Sorry. So this here is V negative. So this is what is called transistor based digital output card. All right. And this is an NPN. In other terms, we call it current sinking transistor output. Current sinking transistor output. So of course you can use PNP. You can use PNP. So this is what is called current perfect current sinking transistor output. Of course, you can have current sourcing transistor output if you replace NPN with PNP. Now, what about if it's a relay? So if it's a relay, let's draw one for relay. So this is where you connect your load. So what you can do, you can connect your load here. Doesn't matter. So you can have your load here, and this is 200 and this can be 120 VAC or 230 VAC. Then the other end, this is now the negative voltage, this is the positive voltage. So again, this is coming from the CPU, and this here is opto isolator. So the signal from the CPU is enough to energize the coil of the relay. So this relay here, this relay. So when this signal coming from the CPU energizes the coil of the relay, then it will move this armature to this side, therefore making the contact and switching the load. Now the good thing with relay, or why most PLCs are relay based output, is because relay is used for both AC and DC switching. That is the advantage of using relay. Transistor only used for DC switching. DC switching, and where you need fast switching, okay? Where you need fast switching. So I think I've explained digital input and digital output cards. Digital input and digital output cards. I think that is well explained. That is well explained. Now the next thing, we want to explain analog input cards. Why we have 14 and why we have 16. Now, remember PLC is a microprocessor, and microprocessor understands 0 and 1s only. So if we connect an analog signal, now let's go back to analog. I think we are done with digital. So let's focus with analog now. This here, analog signal. Now analog signal, I just wrap this here. So analog signals. So we are saying that analog signals, this is what you get from analog signal. If you say that a transmitter is an analog transmitter, let's say that for example, this is an analog transmitter, DMP3 335. This is a pressure transmitter. It's a pressure transmitter, and if you look at the specification of this, look at this here. The output signal is 2-wire 4 to 20 milliamps, or 3-wire 0 to 10 volts DC. This is the specification. This is a very important information that you need to have. Now, so we are saying that analog signals, you can get analog signals in terms of voltage, current, or resistance. So here you can have analog signal in terms of voltage. An example is 0 to 10 volts. Then you can have analog signal in terms of current. An example is 4 to 20 milliamps. 4 to 20 milliamps, all right? 4 to 20 milliamps. Again, you can have in terms of resistance. Let's say you are working with RTD. So this is it's terms of ohms. All right. Now, let's work with 0 to 10 volts range. And your input card is a 16-bit, 14-bit. So your analog input card is a 16-bit, 10-bit, you have 12-bit, and you have 14-bit. Then, what is the need of having all these bits? Why not just work with a 16-bit analog input card? Now, let me explain why. So, you work with 10-bit if you need slow resolution, okay? Slow resolution. And you work with 16-bit if you need high resolution. Now, we say that microprocessor understands 0 and 1s only. So we need a way of converting this voltage into 0 and 1s using ADC. All right, needing with the help of ADC. So this what happens here. So you have ADC here. So this is where you connect your analog signal. So analog signal, you connect it to ADC. Then ADC converts this one, two, three, four, 5, 6, 7. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. That's it. So it converts this, then it takes it to the CPU. So this is a word, 8-bit, okay? It's a word, 8-bit. So it converts the analog signal. It converts the analog signal into an 8-bit, into an 8-bit word. Into an 8-bit word. That is in this format 0, 0, 0, 0, 0, 0, 0. Now, what is the meaning of 16-bit, 10-bit, 12-bit? So this 16-bit, 10-bit determines, this is the size of the ADC. So the size of ADC is 16-bit, 10-bit, 12-bit. Now, this determines the resolution. Let me just explain that. I'll just wrap this. Give me a minute. So this is it here. So we are saying that ADC will convert the analog signal into 8-bit word that CPU can understand in terms of 0 and 1. Now, what's the meaning of 16-bit, 10-bit? Let's start with 10-bit ADC. So 10-bit ADC, that is the size of ADC. So resolution is what? So the resolution will be 1 over 2 raised to power n minus 1. Now this n is the size of the ADC. If it is 10-bit, if it is 16-bit, and if it is 12-bit. So let's get started with 10-bit, and let's take the operating voltage to be, the range to be 0 to 10 volts, okay? So remember, we are working with 0 to 10 volt sensor, 0 to 10 volts. So resolution here for 10-bit will be what? So this will be 1 raised to 2 power 10 minus 1 times the voltage, which is 10 volts. So of course 2 raised to power 10 is 1024 minus 1, that is 1023. 1023, 1 divided by 1023 times 10 volts. How many millivolts is that? Let me just divide here. That is 9 point. So this equals to 9.7 millivolts. So that means that you need 9.7 millivolts just to get 1 bit. 9.7 millivolts to get 1 bit. What about 12-bit ADC? So for a 12-bit ADC, resolution will be what? It will be 10 volts divided by 2 raised to power 12 minus 1 is equals to, so 2 raised to power 12 is 4096 minus 1, that is 4095. So 10 divided by 4095, that will be 2.4 millivolts. What about a 16-bit ADC? What is the resolution? So that will be 10 volts divided by 2 raised to power 16 minus 1. So 2 raised to power 16 is what, guys? 2 raised to power 16 is 65,536 minus 1. Then you get that. Then let's divide by 10. So 10 divided by 65, 535. So that is what? So this is 0.15 millivolts. So I want you to look at the accuracy and the sensitivity. So if you're working with a 16-bit ADC, you just need 0.15 millivolts to change a bit. So this is what will happen. So let's draw a table, just a small table here for 16-bit. So this is the voltage, and this is the digital signal conversion. So of course, if you have 0 volts here, this is 0, 0, 0, 0, 0, 0. If there's a change of voltage of 0.15 millivolts, then that will be 0, 0, 0, 0, 0, 0, 0, 1. It will cause a change in bit. Again, if there's a change in voltage, like now this will be 0.30, this will be 0, 0, 0, 0, 0, 0, 1, 0, representing decimal number 2. Again, if there's a change in voltage, you get 0.45. So this will be 0, 0, 0, 0, 0, 1, 0, 1, 1. So that's how ADC converts analog signal into digital signal. Here. And the meaning of this 8 here, that is the number of channels. It's an 8 channel. So in simple terms, that's just the size of the multiplexer, okay? The size of the multiplexer. That's the number of channels. How many analog inputs can be supported, analog sensors that can be supported by that card. So thank you again. Our next video will explain the concept of current sinking and current sourcing. This is very important when connecting DC devices into your PLC. So thank you again. Subscribe to our YouTube channel and share this video.